Good. So this week, we're going to finish up looking at rational equations. We looked at them last week in section 4.2, but that was more drawing like a sketch. Okay, so this week is going to be focused more on looking at the equation and trying to solve it. When we get to solving inequalities, we're going to use the graphing calculator. Okay, you'll see why when we get to that. So here's an example, to show you, of the kind of equation we're going to solve. What we don't like about that equation is all the fractions. Okay, so the goal, we're not doing this one for quite a while, but when we get probably about 15 minutes, we'll get to it. But when we get to it, the goal is going to be to get rid of all the fractions, so we don't have any fractions left. And that'll make it a lot easier to solve. Most problems that we solve that are going to be rational equations are going to end up being quadratics. So two ways we can solve quadratics. We can try to factor it, or we can use the quadratic formula. Pretty much every problem is going to turn into a quadratic. So the equations, we're going to try solving with algebra. The inequalities, we're going to solve graphically. That's the idea. So we're just going to start with an example. So the example we're going to start with is going to be a problem about distance, speed, and time. To do this problem, you need to know the formula distance equals rate times time. Okay, if you don't remember that formula, well, there it is. You can write it down. But we're going to use that to figure out the first problem we're going to do. Okay, so just to kind of set up the problem before you see it, this problem is going to be about Sue. She's going to be taking a trip, and she's going to use a car and a train to get where she's going. So she's going to drive to a train station, then she's going to get on the train, and the train will take her the rest of the way. To get to the train station, it is 30 miles. So that's the distance that she drives in the car. From there, she gets on the train and finishes her trip. It says, in all, she traveled 120 miles. So, based on that, you should be able to figure out how far the train went. If the car took her 30, the train took her the rest of the way. We'll write that down. We don't know the exact speed of either the car or the train, but all we know is the train was 20 miles per hour faster than the car, on average. And that's our problem. So they're going to ask us to do something with all of that. And I think what they're going to ask for is a formula that represents the time it takes for her to do this trip. Now, there's two things that we don't really know involving the two modes of transportation. Can anybody tell me what's something that we don't know here regarding the car and the train? Yeah? Right. We don't know their speed. So what we're going to have to do is pick a variable for one of them, but we do know the speed relative to each other. We know the train was 20 faster than the car. So let's write a formula that represents the time it takes to complete the trip, and the letter we're going to use is x. And x will represent the speed of the car. Now, x could be the speed of the train. You could have done it that way. You get the same answer. But we're going to let x be the speed of the car. So we're going to write a formula for the time. Now, how many modes of transportation is she using to get where she's going? Yeah?
Yeah.
She's using 2. So she's going to spend a certain amount of time in the car, and she's going to spend a certain amount of time on the train. And we want to find a formula for the total time that includes both. So what would you do with those 2 times to find the total? Yeah.
Use the total distance divided by the rate.
So if you know the amount of time she's in the car and you know the amount of time she's on the train, we would take those 2 times and do what to get the total? How would you combine them? Yeah, you would add them, right? You'd add the 2 times together. So let's just kind of write down the idea of what we're going to do first. So the total time equals, what's the first mode of transportation that she uses? The car. So we need the time in the car. That's part of her trip. And where does she spend the other part of her trip? On the train. So we need the time on the train. Now we have a formula that calculates time. It's right here. Distance equals rate times time. Right now it's solved for D. But can somebody tell me, I'll just put it over here. How would you get time by itself in that formula? Right?
Divide rate by both sides.
Yeah, divide both sides by the rate. And it says distance divided by rate equals time. So now, to find the total time, we want the time in the car, but how do you find the time in the car? Time is distance over rate. So we need the distance in the car divided by the rate of the car. Distance divided by rate will give you time. Plus, how are we going to find the time that she spends on the train? Yeah. Yep, so distance she travels on the train divided by the rate of the train. Rate of train. So now we just fill in those 4 things. 2 distances and 2 rates. All right, so capital T is going to represent the total time, and X is the variable that I'm using. And remember what X is. It's the speed of the car. So let's start with the distance that she travels in the car. Does anybody remember, what did it say she traveled for a distance in the car?
30 miles.
30 miles. So that's the top. 30 over. What's the rate of the car?
We don't know.
We don't have a number for it, but they did tell us what to use for it. It's X. X is the speed or the rate of the car. So distance in the car was 30 over the rate of the car is X. How about the distance on the train? They didn't tell us that, but we can figure it out. How much? How'd you get 90?
Just subtract the 30 from 120.
Just subtract the 30 from the 120, because we know 120 is the total. And we already know she did 30 in the car. So we got the distance on the train. What about the speed of the train? Yep.
X plus 20.
Right, we don't have an exact number, but we know that the speed of the train was 20 faster than the car. So the speed of the train is 20 faster than the car. And there's our formula. So that represents the time that it would take to do this trip. The only thing you have to tell me is how fast was the car going, and I can fill it in and tell you the time. Okay. Any question on how we got that? All right. So you can leave the answer that way. That's one way we can leave it. It's two separate fractions. But if we wanted to put those together as one fraction, what do you need to have if you want to combine them together into one? Yeah?
Common denominator.
Yeah, you need a common denominator. So if you had numbers like that, what would be our common denominator between 5 and 4? 20. So you take each fraction, and to get a 20 over here, you would multiply it by 4, which is the denominator that was here. To get a 20 over here, you can multiply by 5, which was the denominator that was over here. So you end up multiplying each fraction by the other denominator. We can do exactly the same thing there. Multiply each fraction, top and bottom, by the denominator that was in the other fraction. All right. Let's write that down and see what we get when we combine it. What would we multiply the top and the bottom by of this fraction? X plus 20. That's the other denominator. All right, so there's the first one. And the second one, 90 over x plus 20. What would we multiply top and bottom by there to make it have a common denominator? X. So each fraction gets multiplied by the other denominator. I wrote the other denominator in red. Okay, so common denominator is just the product of the two. So in our case, it's x times x plus 20. We could distribute it, or we can just leave it. Okay. What about these first two fractions? What do we get? We did the bottom, x times x plus 20. What do I have to do in the top? Yeah, I have to distribute. Austin, what do I get when I distribute that?
30x
Yep.
plus 600.
Okay. I didn't put it here yet because I might have something I can combine with it, and I'm going to put the final answer right there. If you want to put it here for now, that's fine. Plus, all we have there is 90 times x. So what's going to end up in the top for my final answer? How much? 120x plus 600. Then you combine it together. And that's another way we can write the answer. It just combines it all together. Any questions on that? So let's see what they want us to do with that formula. Okay, but now we have it. I'll copy it on the next page if I didn't already. All right, so it says to find the asymptotes, the zeros, the EBM. Someone remind me, what does EBM stand for? Model, yep, and behavior model. And then the last part is just to graph it on the calculator. All right, so let's start with let's start by writing down the formula that we had on the other page, because that formula has everything combined together. I'm not saying this one isn't good. This is good for some things, but the other one we had is good for other things. So x plus 20, and it was 120x plus 600, I think. Yep. Let's start with the vertical asymptotes. And the vertical asymptotes are the numbers that would make the denominator 0. And there's 2 in this case. Yep.
Can you just scroll up a little bit?
Does anyone see one number that you could plug into the denominator and it would come out to 0? Yep.
It wouldn't be negative x.
It's got to be a number. It's got to be a number. If you plug -1 in here, does it make that a 0? Like if you just just change that to -1, like that, is that number a 0? No. If you plug it in right there, is that number a 0? No. So not -1. Yep. -20. Yep, that is one of them. So vertical asymptote. -20 is one of them. What about the other one? Yeah. 0. So that's something we talked about last week. Vertical asymptotes are the numbers that make the denominator 0. And over 2. Let's see, what else? Find the zeros. Okay, let's do that. The 0 is when you set your formula equal to 0. So like if this was my formula, x minus 5, I set it equal to 0 and solve. That's not my formula, but that's a simple one. You just add 5 to both sides, and that's the answer. This is my formula. It's a fraction. In order to find the zeros, you set that equal to 0 and solve it. So let's write down 0 equals 120x plus 600 over x times x plus 20. So we're setting it equal to 0. And solve. So we've got a fraction equal to 0. How can a fraction ever equal 0? What do you have to do in a fraction for it to come out to 0? Yeah? Like, could you give me a division problem that comes out to 0? Like 8 divided by 4, but that's not 0. I'm looking for something like that that comes out to 0.
If you divide by 0, you automatically get 0.
If you, well, let's try that. So if we take a number like 9, or 99, whatever, divide by 0, the calculator says cannot divide by 0. So how do you get 0 when you divide two numbers? Yep.
You can't.
You can? No, you can. Think about something you can divide and it comes out to 0. Yeah? No, you can't divide by 0. If you try to divide by 0, it won't let you. Yeah.
It goes
Doesn't the numerator have to be 0 to equal 0?
The numerator, what'd you say about the numerator?
The numerator has to equal 0.
Yes. The numerator has to equal 0. That's the only way you can have a fraction come out to 0, is if the top comes out to 0. So when you're trying to figure out what divided by what equals 0, it doesn't matter what's in the bottom. All that matters is if the top comes out to 0, then the whole thing is 0. So set the top equal to 0 and solve it. So, Kiana, what would be my first step to solve that? Yep. And what would be your first step to get the x by itself? This one. Good. You'd subtract 600 from both sides. So we're just trying to figure out what would make the top 0. We do not care about the bottom, because the bottom has nothing to do with making a fraction equal to 0. Just the top. So we subtract that. That's gone. Negative 600 is on the left, and we get 120x on the right. Curtis, what do I do next?
Divide by 120 on both sides.
Divide both sides by 120. Well, 120 divided by 120, that's gone. And negative 600 divided by 120, well, they both have a 0, so we can cross the 0 out. And what do I get for negative 60 divided by 12? Yep.
5.
Yep. What is it, positive or negative?
It will be a negative.
Negative. There you go. And you can check it by plugging it back in, but that works. Negative 5 is the 0. What else do they want? The EBM. Okay, let's do that. So the EBM is when you take the highest degree term in the top. That means you look at the term with the letter, and it's the one with the highest exponent on that letter. And you divide by the highest degree term in the bottom. So there's 2 terms in the top. That's the first one. That's the second one. What's the degree, or what's the exponent on the x in the first term? Yeah? So this is a degree 1 term. This doesn't even have an x in it. So if there's no letter, then that's a degree 0. So what's the highest degree term in the top? 120x. So that was the highest in the top. Now the bottom, you've got to be a little careful. You have to think what it would look like if you distributed that out. And if you want to distribute it out, you could. But if you distributed it out, what would be my highest degree term in the bottom? Yes? X squared. You'd have an x squared plus 20x. X squared is the highest. So 120x in the top, x squared in the bottom. 1, what can I cancel out from the top and the bottom there? So the choices are, if you have a number in the bottom that reduces into 120, we could do that. Or if we have the same letter in the top and the bottom, we can cancel out as many of the letters that they both have in common. Yes. How many x's do we have in the top? Well, right now. 1. How many in the bottom? 2. So there's 1 in the top, 2 in the bottom. We can cancel 1 from the top and the bottom. And what would that leave me with if I do that? Good. 120 over x. So that's the end behavior model. And the end behavior model is used to figure out the last thing that they want, which is the horizontal asymptote. To find the horizontal, well, first of all, it's a horizontal. When you write the equation of a horizontal line, what letter does it always start with? Y. Verticals always start with X's. Horizontals always start with Y. Okay. So Dominic, I think you just said it was Y equals, right? Perfect. To find the horizontal asymptote, you look at the EBM and tell me what happens to the number in that box as X gets bigger and bigger and bigger. Whatever that number is getting closer to, that's the horizontal asymptote. So what happens to that fraction as X gets bigger and bigger and bigger? The fraction gets smaller and smaller, and it gets closer to what? It's getting closer and closer to 0. That's the horizontal asymptote. Now, will it ever be 0? Tyler, why not? Yeah, why won't, no matter what I make this number in the bottom, why won't that fraction ever be 0?
It's like, whatever that is, can never be length.
So what has to happen for a fraction to come out to 0? Kira?
What is the numerator has to equal 0?
The numerator has to equal 0. And what's the numerator in that fraction? It's 120. That numerator is never going to change. So I don't care if you divide 120 by a billion. It's not 0. It's small. But it's never going to be 0. You divide 120 by 10 billion. It's still not 0. It's just getting closer and closer. Any questions on that? All right, let's graph it. Let's see what it looks like. To graph it, you could type in either version of the formula. I think the second one is probably easier to type in because it's all one fraction instead of 2. But it's up to you. So let's type it in, and then I'm going to ask somebody to give me a good window. Okay, so I can see everything. And by everything, I mean the zeros, the vertical asymptote, and the horizontal asymptote. If I can't see that, then it's not a good window. All right, so let's try. If you're going to type it in like the second way, this is how you have to do it. Put in parentheses 120x plus 600. And just to make it easier in the bottom, I would distribute that out. Think of it as x squared plus 20x. You don't have to, but if you don't, you're going to need more parentheses. So I'm going to write it as x squared plus 20x. Now forget that x is actually the speed of a car. Okay, forget about that. Just pretend that all you have is this equation. So I don't care if you use negatives, positives, use anything you want. What would be a good minimum for my x values? Yep.
I just want to see how you typed it in. I just
So just like that. Except there's a parenthesis in front of the 120. And so Cameron, what would be a good x min? Okay, why'd you pick 120? Do we have, out of the things that I have here, vertical asymptotes? And make it smaller so we can see it. the zeros in the horizontal asymptote. We're not really worried about the horizontal asymptote when we're setting the x min. Is there anything important that happens below 120 on the x-axis? What?
The vertical asymptote is -20.
We have a vertical asymptote at -20, so we need to see -20 on the screen. If we set the minimum at 120, we're going to cut that off. So where should we set our minimum?
-20.
And let's make it so the asymptote isn't right on the very edge. Let's go past it. I would say maybe -40. How much past it you go is kind of up to you. But actually, I already have it typed in, -40. X max, well, we definitely want to make sure we see 0. But I wouldn't stop right at 0. I would go a little past it. So let's try 40 and see how it works. Now, the y min and max, we don't really know. I'm just going to leave it at -10 to 10. I'm going to try that. And if it looks like I can't see everything on the screen, I'll go higher or lower. Okay, but that's the standard window for the y's. Let's hit graph. And I think that's actually pretty good. A pretty good sketch. So the important things we want to be able to see are, where does it cross the x-axis? That's the 0. It should cross at -5. Look at my graph. I know it's a little hard to see, but does it look like it crosses at -5? What do you think, Sam? What do you think? Yeah. You can't really see it too well, but if you count 1, 2, 3, 4, 5 to the left, yep, that's where it crosses. There should be a vertical asymptote at 0. That would be a vertical line right there. And I can definitely tell that the graph is getting closer and closer as it goes down. And if I went up higher, I would see it getting closer and closer. So there's my first vertical asymptote. There's another vertical asymptote at -20. So that's -5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 20. About right there. I think that's 20. So if I were to zoom down more, I would see those getting closer and closer. And if I zoomed up a little bit more, you'd see those getting closer and closer. So that's a pretty good window. If anything, I might go a little higher and lower, just so I can see it getting closer. But that's not bad. What's that?
30, 40.
Yeah, you might, you go a little bit more, but what we had it isn't bad. Right? If you wanted to make it even better, we could try -40 to 40. Now that's even better. Now I can see it getting really, really close to the axis, and I can see it getting much, much closer to -20 because I'm zoomed down here. So that's a little better. But that's okay too. So what we would write for the answer would be those numbers. Tell me the x min and the x max that you use. And tell me the y min and the y max. What's that? You could write it exactly the way it's written right there. Just exactly like you see. The other numbers you don't have to tell me. Just the 4 that are in the box. Now, what did x originally represent? Oh, now I want to think, speed of the car. When you're talking about the speed of something, what kind of numbers would make sense? Positive, right? You wouldn't have negative numbers. So if we were focusing on the part of this graph that actually relates to the word problem, Negative speed wouldn't make sense. And what about time? Time is my y value. Do negatives make sense with time? No. So the only part of this graph we would really be looking at, if we were focusing on the word problem, is the part that's in quadrant 1. That's the part we would focus on. These other two parts to the graph have absolutely no meaning in relation to our word problem. They don't make any sense at all. But that's okay to show them because that's what the problem was. So now it says that Sue has 2 hours to complete the trip. I want to find the speed that she must be driving at to make sure she completes the trip in 2 hours. But I just want to do it graphically. First thing I need is the formula that we already figured out for time. Can somebody tell me again, what was my formula for time? Give me the version where it's all combined together. Yep.
120x plus 600
Okay, good.
over x parentheses x plus 1.
Okay. So this is the formula to complete the trip, the time to complete the trip. X is the speed of the car. And they're telling me a time. They're telling me 2 hours. So where is that 2 going to get plugged in? Where the t of x is. So change that to a 2. So now you're going to have 2 equals. Keep everything else on the other side the same. Well, I already have the right side typed in. Okay, that's already in y1 in the calculator. Where do you think I'm going to put the 2? Yeah, we're going to put it in y2. So essentially, we're going to graph a horizontal line at 2. We're going to graph what we already had before. And what do you think I'm going to look for? I'm going to look for where they intersect. But this time, since we're talking about the word problem, I don't want to confuse myself by looking at negatives, because negatives are not part of the word problem. So let's just focus on quadrant 1. So there's the part that we had in quadrant 1. Okay, I can't tell, I don't think we've gone over enough to see where they intersect. I also think we've gone way too high. I don't think we need to be looking all the way up here. We could probably even look at like half of it. Okay? Or even just up to 10, I think is going to be plenty. So let's set the speed of the car a little higher. And let's set Ymax lower. So hopefully we get a better zoomed in picture of what's going on. I think we're okay now. Yep, we're fine. So the blue is the formula, and the red line is 2. How do I see where those cross? Second, and then what? Trace. And which option do we want? Intersect, yeah, option 5. So first curve, second curve, and then yes, I just hit enter each time. So what is the speed that Sue was driving at to complete the trip in 2 hours? What's the speed she was driving at? 46.46 miles per hour. There's your speed right there. And that's how you find it. Any questions on a lot of graphing calculator stuff at the end here, right? Any questions on how to type any of that in? How we did the intercept? you have a question, Jenna?
I'm just confused.
Did you get that graph?
No.
Did you?
I typed it in wrong.
So you would want to make sure you type that. Can't see it, but that should be a parenthesis. Is that what you typed in?
I just didn't do the x squared. I had like the x on the outside.
Okay.
But
Anyone else having trouble getting that picture? Okay, so what we did there, that would be considered more of a graphical approach. Okay, graph two things, use the calculator to find where they cross. Okay, it's 46.46 miles per hour. So what I want to look at now is doing something similar, but without the graphing calculator. Solving an equation that has a fraction in it, and it has variables in the bottom. Yes? Yeah. Okay. I'm going to just change this a little bit. So this is solving rational equations.
no.
Yes? So solving rational equations. The goal is to eliminate the denominators. That's what basically makes a rational equation hard, is that you have fractions. If we can eliminate the denominators, then it's going to become easier. So to do that, this, we will, I'm just trying to make it blend into what I have here. We will end up, or I'll just say we will multiply both sides by a variable. So to eliminate the denominators, we're going to end up multiplying both sides by a variable. It's okay to multiply both sides by a variable, but when you do that, something could happen. What you could end up doing when you multiply by something with a letter in it is you may create an extra answer in the problem that shouldn't be there. Okay. That's called an extraneous answer or extraneous solution. It's not because you did anything wrong, but it's because some of the steps you took involved multiplying by a letter. It created an extra answer. So how do you avoid that? Well, you can't. You may end up with an extra answer. What you can do is after you get the answer, you check and you see if it works. If you plug it back in and it doesn't work, then you know it was extraneous. Generally, what's going to happen in our kinds of problems is when you try to check it, it's going to cause you to divide by 0. You can't divide by 0. So if you plug a number back in and it causes you to divide by 0, we're going to cross that answer out and say that it doesn't work. If it doesn't cause you to divide by 0, then it's okay. But that's going to be the goal. We're going to eliminate the denominators, and we're going to do it by multiplying both sides by something with a variable. I can't tell you exactly what we're going to multiply by because every problem is a little different, but it's going to be a variable. And just about every problem that we do where you multiply both sides by a variable is going to end up being a quadratic equation. So specifically, what do you multiply each side by? The LCD. That's what you multiply by to get rid of all your fractions. Here's an example with numbers. Say you had to solve x over 3. Again, you just watch me write this. Plus, say, 4x over 5 equals, I don't know, 8/15. That's not a hard problem to solve if it wasn't fractions. It's pretty straightforward. It's the fractions that are messing us up. So what you want to do is look at all three of your denominators and find the smallest number you can that 3, 5, and 15 divide into. 15. So in this particular problem, you'd multiply everything by 15. And I'm not going to finish the whole thing. I just want to show you what happens. How many times does 3 go into 15? 5. How many times does 5 go into 15? 3. And how many times does 15 go into 15? So now you're left with something much simpler than what you started with. 5x plus 3 times 4x equals 8. It's a much easier equation to solve now that it doesn't have all those fractions in it. So it would just be 17x equals 8, and then divide by 17. Yeah. Yeah. We're going to try the same exact idea on this problem. The only thing that's making that more difficult than it needs to be are all the fractions. So we're going to look at each denominator, and we're going to try and find LCD, just like we did with the numbers up above. So it's 2x over x minus 1 plus 1 over x minus 3 equals 2. And then in the bottom is x squared minus 4x plus 3. Now, whether or not you noticed up above, there was a special connection between the number 15 and the other two denominators. What's the connection between 3 and 5 and 15? Yeah? If you multiply these two denominators together, it gives you this denominator. That's exactly the same thing right here. You can check it, but if you FOIL x minus 1 times x minus 3, you get x squared minus 3x minus 1x. That's minus 4. And then negative 1 times negative 3 is positive 3. So I'm going to put that down below, just to remember. That x squared minus 4x plus 3 is really x minus 1, x minus 3. So now, put these in parentheses. Does anyone see what I could multiply all three of those by? And it would cancel out every denominator.
X squared minus 4x plus 3.
And can you tell me what you just said? If you say it factored, what is it?
X minus 1 times x minus 3.
Perfect. We're going to multiply everything here by the product of the two denominators that were right there. Just like we did up above. We multiplied everything by the product of 3 and 5. Let's multiply everything by the product of x minus 1, x minus 3. So first one, second one, and the third one. If you pick the right thing to multiply by, something is going to cancel in every one of these. Just like here, something canceled, that's why I drew a line, in every part. So this first one, if you wanted to write it out properly, I'm not going to rewrite the whole thing, but this is what you basically have. 2x times x minus 1, x minus 3, over x minus 1. That's what this first fraction should look like. What's going to cancel out here? Yeah? The x minus 1. That cancels out completely. What cancels out in the second fraction?
The opposite.
Which one?
The x minus 3.
Yep, the x minus 3 cancels out. And what cancels out in this third fraction? This guy? Both. This whole thing cancels out. So every denominator is gone. When you clean up what you have here, you're not going to have any fractions left. You're going to have some distributive properties. 2x times x minus 3. That's the first one. What's 2x times x? 2x squared. And what's 2x times negative 3? Negative 6x. That's the first one. Now the second one, you're distributing this. This symbol goes with that number. Positive 1. So positive 1 times x, positive 1 times negative 1, well, nothing happens. Because we're just distributing a 1. So x, and then positive 1 times negative 1, negative 1. And what's on the right side? 2. Just for number 2. So now, if we look at that, what kind of equation is that?
Michael's better now.
It's a quadratic. So now we got rid of all the fractions. Highest exponent's 2. So now it's a quadratic. So we got to get everything on one side and then try to solve it. Okay, so when we're solving a quadratic, what do we want to get on one side? 0. So we want to put everything on the other side. I also have some like terms. What's negative 6x and 1x? So that's negative 5x. And let's bring the 2 over. What's negative 1 minus 2? Negative 3. And that is factored. So we don't need to use quadratic formula for that. So let's see if we can factor. So we need 2 things we can multiply together to get 2x squared. 2x and x. Perfect. Now I have a minus and a minus. So what does that mean my signs are going to be here? One of each. Okay, a plus and a minus. It does make a difference which one we put where. My suggestion, I think, would be that. If you get them wrong, just try to switch it. Now we need 2 numbers that multiply together to give me 3.
3 and 1.
3 and 1. I would do them in the other order. 1 and 3. And let's see what happens. 2x times x is 2x squared. So that's good. 2x times negative 3. That's negative 6x. 1 times x is positive 1. Negative 6 and a positive 1 is a negative 5. Perfect. So now we've got something times something equals 0. So set each one of those equal to 0. And those are my answers. Either that's 0 or that's 0. What do I get if I solve the first one for 0? Yeah? Negative 1/2. And what do I get if I solve the second one for 0? 3. Yeah, you just have to make sure that those answers work. And by work, that just means make sure when you plug it back in, it doesn't cause you to divide by 0. If it does cause you to divide by 0, cross it out. So negative 1/2 and positive 3. Let's go back to our original problem. Let me move away the stuff we added so you can see the original. So do both of those answers work? Negative 1/2 and positive 3. Could I plug them back in the bottom? Yeah?
Would you not be able to do 3?
I cannot plug 3 in.
Okay, so the middle one would be 3 minus 3 and that would be 0.
Right, the middle one would be 3 minus 3, which would give me a 0 here. And 3 minus 3 would give me a 0 in this one too. So 3 is what we call an extraneous solution. It's an answer that works in the equation that we made by solving the problem, but it doesn't work back in the original. So we cross it out, and we can label it extraneous. So what I might set up on the test is I have 2 boxes for this problem. One box would say, this answer is extraneous, and you put the answer that's extraneous in the box. You'd put 3. This answer works, and then you'd put negative 1/2. So there's 3 things that can happen. You can get one answer works, one answer doesn't. You can get both answers end up working. That's the second thing. Or you can get both answers are extraneous. If both answers don't work, then you just write no solution. Nothing works. Any questions on that? Especially the factoring at the end. Any questions on that? All right, so I think what we'll do, we'll try one more of those. And then the graphical ones, we already did something graphically, but I'm going to save this for tomorrow. So let's finish up with this one. So solve algebraic. Now, I want to look at that first and see, does it have the same pattern as last time? Is denominator 1 times denominator 2 equal to denominator 3? Yes. It is, yes. This is x times x plus 2. That doesn't have to always happen, but it will always happen in the problems that I give you. Okay. So make 3 sets of parentheses. And can somebody tell me what we would multiply every fraction by to cancel all my denominators? Chris?
X plus 2.
X plus 2. So put an x plus 2, x plus 2, x plus 2. Before you do anything out, cancel out what is in common with the top and the bottom. Okay. First fraction. Is there anything that's in common there? If not, then we did it wrong. X. Second fraction. Is there anything that's in common there? Yeah. X plus 2. And third fraction. All of it. So we can do the right-hand side pretty quick. What do you have left there? Yeah? Yeah.
3x plus 6.
No, just the right side. Just negative 6. That's all that's on the right. Now on the left, you have x minus 3 times x plus 2. That's a distributive property. So you have to FOIL that up. Because that's in parentheses and so is the other one. So x times x is going to give me x squared. What's x times 2? 2x. What's negative 3 times x? So we can combine these together right now. What's 2x minus 3x? Negative x. And then negative 3 times positive 2. Negative 6. That's going to be nice in a second. You'll see why. And then here, positive 3 just times x. 3x. Okay, let's combine the like terms. So x squared. What's minus x plus 3x? 2x. And now that's a quadratic equation again. I told you these almost always turn into quadratics. What do we want to get it equal to? 0. So how do we move this negative 6 to the other side? Add 6. So x squared plus 2x. What's negative 6 plus 6? 0. This is gone. This is gone. Now that we only have 2 terms left, you don't have to use the 2 sets of parentheses to factor. All you have to do is factor out the GCF. What do both of these terms have in common? X. And if you factor that x out, what's left inside right there? X plus 2. Now we're at the last step. Set each one of these equal to 0, just like we did right here, and then solve them. See if they both work, if they both don't work, or see if one of them works and one of them doesn't. Okay, so set both factors equal to 0. Well, when you set the first one equal to 0, there's nothing to solve. Set the second one equal to 0. Negative 2. Good. Those are my 2 possible answers. So go back up and make sure that they don't cause you to divide by 0. And if you can't see what's in the bottom, there you go. Can we plug 0 back in?
No.
No. That would cause you to divide by 0 right there. Can you plug negative 2 in? No. Negative 2 would cause you to divide by 0 there. So what that means, both of the answers to this problem are extraneous. There is no solution. Any question on that? So that's the hard part, doing the algebra. The easy part is graphing something on the calculator and solving it. So that'll probably take about 5 minutes. We'll finish that tomorrow. And then we'll do 4.3. We have 3 days to do it. So we'll start the test halfway on the 3rd day. So we got plenty of time. Let me just change that a little bit. So let's do 1 through 9. Do that. Let's do 20. Okay, and I'm just going to give you a hint. On number 20, that is not one that you can do by hand. It's kind of like the bike, not the bike problem, the Sue problem, where she traveled by train and car. You're going to use the graphing calculator. for number 20, and you're going to calculate an intercept. That's how you do it. 24. Yeah, that one is also on the graphing calculator. So 1 through 9 odd, 20, 24, 28, and 31. Okay, we'll take a look at that tomorrow.